Most shelter builders get it wrong, not because they don't care, because they learned from someone who was also doing it wrong, and neither of them stopped to ask why the foam goes where it goes. Waverly Oaks figured out the right answer by coming at it sideways. She was 22, living under a stretch of overpass on the eastern edge of Kansas City, and she had never taken a building class in her life. There she had a circular saw borrowed from a guy, 2 spots down, a stack of salvaged 2x2 framing lumber she'd pulled from a gutted apartment building, and a disagreement with every other shelter she could see from where she was standing. The disagreement was simple. Those shelters rotted. Hers didn't. 3 winters in, she was still in the same structure. Most of the others had built twice, some had built 3 times. The foam goes on the outside, not tucked between the studs, on the outside of the frame, covering the whole wall. The reason most people don't do it that way has more to do with what gets sold at hardware stores than with what actually works. Her Waverly grew up in Reno. Her family rented a duplex on the north side of town. 2 bedrooms, a small backyard with a broken gate her dad kept meaning to fix. Her mom worked dispatch for a trucking company. 12-hour shifts, irregular schedule, the kind of job that pays just enough you don't go looking for another. 1. Her dad was in and out, and then mostly out after she turned 15. She had a younger brother, Cody, 7 years behind her and needing things the way 7-year-olds do, constantly and specifically. For a while, things were tight but workable. Waverly picked up hours at a sandwich counter near the high school. Cody got school lunch. The duplex stayed. She was 19 when her mom's hours got cut to part-time and the duplex stopped being an option. 2 months' notice. Her mom moved in with a cousin in Sacramento and took Cody with her. Waverly stayed. She had reasons to, or reasons not to go, or both, and it doesn't matter to this story. She moved in with a friend for a few months, then a different friend for a few weeks, then nobody. By 20, she was in a tent near the railroad tracks on the outskirts of a Reno encampment, in a spot that flooded whenever it rained for more than an hour. The railroad runs through a low section of that part of town, and water comes from 3 directions when the drains back up. She doesn't call that period a crisis. She calls it cold. Cold and wet in a way that makes everything else harder. You can be tired and still think. You can be hungry and still plan, but cold and wet at the same time puts you somewhere below both of those, where thinking feels far away and the most concrete thing in the world is wet sleeping bag against your back at 3 a.m. Bought a cheap dome tent from a dollar store in the first year. The poles bent in the 3rd month, the fly leaked by the 4th. She got a better one second-hand, good brand, mostly intact. That one lasted about 6 months before the floor seam failed. The problem wasn't quality, it was condensation, wind, the way moisture creeps through seams and pools at floor level and wicks into everything it can reach. She was 21 when she moved to Kansas City. She had a reason, a connection, the possibility of work through someone she knew. The job dissolved inside 2 weeks, but she'd looked at the encampment under the overpass on the east side and decided it was better than where she'd come from, more established, or a few people who'd been there for years. An unspoken set of rules about spacing, about noise, about not burning things too close to the bridge support. She set up her tent and watched what happened to the other structures through that first winter. She paid attention the way you pay attention when the stakes are also whether you make it to March without a major problem. What she saw was a pattern of the same failure happening in different shapes. Several people in the encampment had gone past tents into stick frame shelters. They'd figured out, through experience, through watching what held and what didn't, that a rigid frame handles wind better than tent poles, that something bolted together resists collapse in a way that fabric over metal rods doesn't. They'd built frames from whatever they could find: salvaged lumber, pallet wood, the occasional 2x4 from a construction dumpster. They'd insulated those frames with foam panels, rigid foam board, mostly the pink or gray stuff you find at hardware stores or salvage warehouses, pushed between the studs, cut to fit each stud bay, pushed in snug, the whole interior then covered with poly sheeting or emergency blanket material. That's how the tutorials do it. Between the studs is the standard method. The problem is the studs themselves. Wood conducts cold. Not as fast as metal, but it conducts. Every stud in the frame is a solid path from the exterior face of the wall to the interior face. When you fill the stud bays with foam, you've insulated 14 out of every 16 inches of wall. The other 1.5 inches, the stud itself, is doing nothing except conducting. Outside cold touches the stud face. The stud pulls that cold through to the inside surface. And because that interior stud face is now colder than the air around it, moisture from the interior air condenses there. Every night. All winter. Their building science has a name for this: thermal bridging. The stud bridges across the insulation layer and carries cold through. In a house, this is manageable. A house has multiple layers of protection outside the stud cavity: sheathing, weather-resistant barrier, siding. That assembly reduces how much cold air contacts the stud directly. The bridging still happens, but it's diminished by everything sitting between the stud face and the outside air. A camp shelter has one layer of plastic sheeting as its exterior skin, nothing protecting the stud face. The cold hits the stud directly. The stud hits the interior surface directly. One winter of that is the beginning of soft wood. 2 winters is the beginning of structural movement. Waverly didn't have that vocabulary. She had the outcome. She put her hand against the inside wall of a nearby shelter. One morning in January, after a week where the temperature hadn't broken 25 degrees, the liner was cold where she expected it to be. But where the studs ran, it was colder. She could feel the difference through the liner. She pushed the liner aside and touched the stud face, and it flexed, just slightly the way wood only flexes when the fiber has started to soften. She didn't say anything to the man whose shelter it was. She stood there for a minute thinking something like, "This wall is cold in lines. The lines are where the wood is. The foam is working. The wood isn't." She went back to her tent. She thought about it for 3 days. The idea came from the wrong direction, from her jacket, not from the shelter. The green canvas jacket she still wears most days. She'd sewn a layer of thin foam into it the previous winter, cut from an old camping mat she'd found, sliced into panels, hand-stitched inside the jacket at the chest and upper arms, where she'd placed the foam between the shell and the lining, in the spaces between the seam lines. On cold days, she could feel exactly where the seams ran. The foam panels were warm. The seams weren't. She'd assumed that was just a limitation of the method. The seams are what they are. 3 days into thinking about the shelter walls, she made the connection. The foam in her jacket was between the seams exactly the way the foam in the shelters was between the studs. The seams were cold for the same reason the studs were cold. They were gaps in the insulation, solid material running from outside to inside with nothing covering the break. If she put the foam on the outside of the jacket, over the seams, not between them, the seams wouldn't matter. The whole surface would be covered. The seams would be behind the foam, protected, not bridging. She applied that to the wall. If she ran the foam across the outside of the frame, covering the studs along with everything else, the studs would be inside the insulation layer, protected. The thermal bridge would be broken at both ends. She started planning the build that spring. The lumber took about 6 weeks to accumulate. Demolition happens constantly in any city, and when you're paying close attention, you learn where things land before they get hauled away. A gut renovation a few blocks from the overpass put a stack of salvaged 2x2 studs on the sidewalk on a Thursday morning. She moved them in 2 trips, leaning them against the bridge support column to dry out. More came from a pallet company that burned boards of non-standard dimensions. She talked the yard guy into setting aside usable lengths for a week while she figured out pickup. Some she bought with day labor money from a building supply store that sold culled lumber out back at a fraction of the normal price. Day labor in Kansas City pays between $60 and $85 depending on the job. She put roughly $45 of it toward lumber on the days she worked. It took her 4 separate purchases to get the count she needed, spread across 6 weeks of whatever work was available, landscaping mostly, some loading, one day moving furniture up 4 flights in a building that hadn't got its elevator permit yet. She drew the frame on a piece of paper bag, a rectangle 8 feet by 6 feet floor plan, 6.5 feet at the peak, pure shed roof, single pitch, high-end angled toward the overpass support column to use it as a partial wind block. 4 wall frames, simple construction, corners connected with carriage bolts. Every joint got a 3-inch deck screw as backup. She spent 2 days just planning the frame before she cut anything. Not because the frame was complicated, it wasn't, but because she'd learned from watching other people build that the mistakes happen when you're moving fast and you're sure you know the next step. And she drew the wall frame separately, labeled each member, wrote the dimensions twice. She cut test pieces from the worst lumber first to check her saw angles before she touched anything she needed to keep. The frame went up in 4 days. She worked alone. Two of the wall sections she had to prop temporarily with scrap lumber while she drove the bolts. She did it standing on a 5-gallon bucket. She checked each column with a borrowed level twice before moving on. The roof sheathing was 3/4-inch plywood from a construction dumpster, with most of its surface intact. She waterproofed it with 2 layers of roofing felt, peel and stick membrane over every seam, then a 3rd layer of felt over the top. The membrane had been mostly unused in the same dumpster as the plywood. The roof was the part she felt best about. It sloped correctly. She'd measured twice and still held her breath the first time rain fell on it. The water ran off clean. No pooling at the low edge, no backup at the peak. She watched it from outside for 20 minutes in a light drizzle and went inside feeling like the worst risk was behind her. Then she thought about the walls. The Restore on Troost Avenue in Kansas City is the kind of place you have to slow down in. Habitat for Humanity runs it. Contractors and homeowners donate leftover materials. The store sells them cheap. The proceeds go toward construction. There's too much to process if you try to walk through fast. Aisles of lumber, racks of windows, cabinets without hardware, doors without frames, bins of plumbing fittings sorted roughly by type, and foam board. A whole aisle of it sorted by thickness, mostly 1-inch and 2-inch panels, mixed manufacturers, some foil-faced, some not. Priced at roughly 40% of what the same panel costs new from a hardware store. She'd been in there a dozen times before she started building. She knew the foam aisle, or she'd assumed foam between the studs, the standard method, because that was what she'd seen and what made visible sense when you looked at a frame. The studs are the structure. The foam fills the gaps. She bought 8 panels the first trip, 1-inch, foil-faced on one side. She put them in the cart and walked them out to the parking lot, and then stood there a while with them leaned against the wall, not inside the studs. That was the thought. Outside, if she ran the foam across the entire exterior face of the frame, covering the studs and the sheathing, as one continuous surface, there would be no break, no cold stripe, no stud exposed to outside air. The foam would protect everything behind it equally. She stood in that parking lot for a few minutes. People walked in and out around her. She took the panels back inside and found the guy working the floor and asked whether they had furring strips. He pointed her to the lumber section she bought. 14 pieces of 1x3 lath. She came back, bought the foam again, loaded everything into the cart, and walked back to the encampment thinking about the problem the whole way. Furring strips are thin wood lath, 1x2 or 1x3, used to create a standoff layer between two surfaces. In standard construction, they're used for drainage planes, or to give siding a surface to fasten to, or to level out a wall that isn't flat. They're not structural. They're positional. Her plan, foam panels across the outside of the entire wall frame, joints overlapping, every seam sealed with aluminum HVAC tape so the layer was continuous. Then furring strips run vertically over the foam, screwed back through the foam into the studs behind it. The screws would pull everything tight and hold the foam in place permanently. The furring strips would sit, slightly proud of the foam surface, creating a narrow air gap between the foam and whatever outer skin she put over them. That air gap matters more than it sounds. A wall sealed completely with no way for moisture to move creates a trap. Condensation has nowhere to go. A thin air gap behind the outer skin gives vapor a path out. The wall can breathe in the places where the outer skin has small gaps at top and bottom. The foam in the frame behind it stayed drier. She didn't read this anywhere. She worked it out from thinking about where water goes when it can't go anywhere. The outer skin was corrugated polycarbonate roofing panels. A man named Dale, clearing a storage area on a farm outside the city, had 22 panels he didn't need. He sold the lot for $20 and helped her load them. She washed them at a spigot behind the Restore, stacked them flat to dry, and ran them over the furring strips with self-tapping screws, overlapping each panel 6 inches at the joints. 2 days of work. The whole exterior was done. The interior went up in October. 1 layer of 6mm polyethylene sheeting stapled to the inside face of the studs and pulled tight. Every seam overlapped 4 inches and sealed with the wide aluminum tape. The tape is not optional. Poly sheeting is continuous, but the seams aren't unless you seal them, and an unsealed seam is a path for warm interior air to contact a cold surface and leave its moisture there. She had a battery lantern, a sleeping platform built from pallets surfaced with a piece of salvaged plywood, and a small propane camping heater she used on the coldest nights. Only, the heater was backup, not the main system. The first hard freeze came in December. She woke up that night outside somewhere in the low teens and pressed her hand against the interior poly sheeting. Cool, not cold, not what comes through a wall that's failing. She'd built a small inspection panel into one corner, a square of foam she could pull out and replace, so she could check the stud face without opening the wall. She pulled it out. The stud face on the interior side was cool, not wet, not frost. The foam had done what she needed it to do. The cold was stopping at the foam and not reaching the wood. In the shelter, 12 feet away, the one Todd had built over the previous summer, she could see frost on his interior liner the next morning. Not frost from cold air inside. The air inside wasn't that cold. Frost on the back of the liner where it touched the stud face. The stud was below freezing on its interior side. The liner was in contact. The temperature of that surface crossed the dew point of the interior air every night, all winter. That frost is the beginning of rot. It's the thing you don't see clearly until the stud flexes under your hand in March. She watched his wall that whole winter and the following one. The slow darkening at the base of the studs, the frame losing its rigidity by degrees. He was replacing structural members before his second summer. She was adding shelving. Her second winter was the one with 19 nights below 15 degrees Fahrenheit and 3 ice storms. The ice storms were the kind that coat everything in a solid half-inch glaze and don't melt between nightfall and morning. The kind where the encampment goes quiet because ice is loud enough coming down that there's nothing to do but wait it out. Between the ice storms, the temperature climbed just enough to partially melt the edges of things and then dropped again at night, which means everything refroze with a harder shell the second time. The tarps and tent fabrics in the encampment crinkled when they moved. The ground between shelters turned into a skating surface. People were careful with their feet for about a week. The third storm put real weight on the roof. She was inside when it built up. She listened to the corrugated panels flex slightly under the load and didn't move. Not from false calm, from having put 3/4-inch plywood on that roof and sealed it properly and checked the slope 3 times before she'd called it done. The roof held. The ice came off in sheets when the sun hit it the next morning. She'd left clear zones on all 4 sides when she planned the footprint, and nothing was stored in them. The sheets hit the ground, and that was it. The interior temperature on the coldest night that winter dropped to 36 degrees with the heater off. Cold. Not dangerous if you have proper bedding and you're dry. Her sleeping bag, rated to 20 degrees, was working well inside its range, staying loft instead of slowly compressing from being used at the edge of its capacity every night for months. That's a real difference. Gear that works inside its limits lasts. Gear pushed to its limits doesn't. 3 of the 5 other stick frame shelters in the encampment had failure events that winter. A roof section came loose in the second storm. A ground frame rotted at one corner, and the whole structure shifted out of plumb. One person's phone blew out from between 2 studs, and the cold came through that base so fast they ended up sleeping at the overnight shelter down the street for 2 weeks. While they figured out repairs, she fixed a draft under her door. Foam pipe insulation slit lengthwise down the middle, pushed over the bottom door edge. 20 minutes of work. By the third winter, people came over to look. Not to be taught. Nobody in a camp setting wants to be taught anything. But there's a difference between a structure that's holding and one that isn't. And after 3 winters, it was obvious which one she had. People would stand outside and look at the wall and ask something precise. How are the foam panels held? Why doesn't your roof leak at the panel seams? Where did the corrugated stuff come from? She'd answer what she could. She doesn't use the thermal bridging language. She doesn't have it. She says, the foam goes on the outside so the wood stays dry. She says, when the cold gets to the wood gets wet, and wet wood moves. People hear that and nod and leave. One afternoon, Marcus was there for one of those conversations. He'd been in commercial construction before his situation changed. Site supervision mostly. Big framing projects on the commercial side. He stood and listened to her explain the outside foam method to someone else, and then was quiet for a minute and said, that's a continuous exterior insulation system. He said it like he was matching a face to a name he hadn't seen in years. Sure, he said they use it on commercial buildings now. High-performance envelopes. Energy codes are catching up to what the physics always said, and old buildings are being retrofitted because continuous insulation outperforms the between studs method in any wall assembly where the stud faces are exposed to significant cold. She said she didn't know any of that. He said it didn't matter how you got there. He came back 3 times over the following weeks to look at the wall more carefully. He pulled on the furring strips to check how they were anchored. He looked at the seam tape on the foam layer. He checked the bottom edge of the exterior panels for water entry. He found one section where the foam joints at a corner weren't fully taped and the HVAC tape had lifted slightly on one edge, a seam she'd missed when she did the original inspection. She fixed it that afternoon. He helped her add a second foam layer that spring, 2-inch polyiso panels over the original 1-inch foil-faced foam, another pass of furring strips, a new outer skin over everything. The wall got substantially thicker. The following winter, she used 3 fewer propane canisters than either of the previous 2 years. Total material cost across the whole structure and all additions, $183 over 2 years. The lumber was mostly found. The screws and bolts were the biggest cash expense after the foam. The foam across 2 restore trips cost $64. The shelters around her, built by people with more experience and sometimes better access to materials, cost more and lasted less. The reason this doesn't travel through the survival shelter world isn't complicated. Foam panel manufacturers sell foam with installation guides. The guides say between the studs because in a full residential wall assembly that method works fine, and it uses more product. Closer fits, more cuts, more waste. A continuous exterior layer on a small frame uses less foam, can be done with offcuts and irregular pieces, and doesn't push anyone toward buying new material. Or survival shelter tutorials learned from residential construction conventions, because that's where the accessible information lives. Those conventions were developed for wall systems with multiple protective layers outside the stud cavity. Her A-camp shelter has one. The convention doesn't carry. Nobody is hiding the correct method. The building science literature on continuous exterior insulation exists, and it's not buried, or it's in passive house guides, in commercial construction manuals, in energy code analysis documents. It just isn't aimed at someone living under a bridge in Kansas City with $64 to spend. Waverly found it by thinking about the seams in her jacket. If you want to actually feel what she built, try this. Get 2 pieces of rigid foam board, any thickness 12 by 12 inches each. Get a short piece of 2 by 2 about 12 inches long. Cold morning, below 40 degrees. Make 2 assemblies. In the first, put the wood in the middle and a foam panel on each side, sandwiching it. This is the between studs model at small scale. In the second, stack the foam panels flat and put the wood behind them so the foam faces out and the wood is protected. Put both outside for 20 minutes. Come back and press your hand flat to the interior face of each one. On the first, you'll feel the colder line where the wood passes through. The foam sections are warmer. The wood line is distinctly colder. You can feel the exact width of the stud running through the insulation. On the second, you won't feel that. The foam face is even across its whole surface. The wood is behind it and the foam has done its job. That's all of it. 2 pieces of foam and 20 minutes outside. Her structure turned 30 months old in the 3rd winter. That spring, she pulled the inspection panel and looked at the stud face that had been behind the exterior foam layer for 2.5 years. Dry, grain tight. She knocked on it and it knocked back solid. She's planning a small addition this summer, a covered porch section on the north wall, mostly for gear storage. Same build method, outside foam, furring strips, corrugated skin. She's been thinking about whether to run the foam continuously around the corner joint between the existing wall and the new addition, or treat them as 2 separate envelopes that connect at the door. Continuous is correct. A break at the joint is a cold spot at the joint, which is a condensation point at the joint, which is where failures start. The execution is more complicated, cutting foam around a corner, keeping the vapor layer unbroken through the connection. But she's done harder things. She's going to do it right. She already knows what wrong looks like. She watched it fail in 3 winters of other people's structures. She's not building that again. The next thing to know about what she built is the floor, because the floor is where most people in a small structure lose the most heat, and almost every tutorial skips it or mentions it briefly and moves on. What she did under her platform is different from anything else documented in this context. Same principle, different surface, different problem.